Okay, so the previous two series that we looked at were specific in name and in structure. That's typically not the case. Those are the two that we can name. Um, Typically what will happen is you'll have a series, you can't really label it, and you'll use one of several tests that we're going to introduce. And I'm going to introduce the first one today. It's called the divergence test. And I'm going to write it out first. So let's do that. So for any converging series, such as, I'll write this totally generic, I'm just going to call the terms the ANs, A1 plus A2 plus A3. If this series converges, there is a fact that is indisputable, and that is that the individual terms that you're adding up go to zero. And I just want to, so that's not the test, that's a statement. The test will come here. Just to illustrate why this works, and don't feel compelled to write this down, but I think it illustrates how the test works. Let's see. Let's use let's use this example. Okay, that's 2n squared over 2n squared plus 1. So I'm going to have, individual terms. I guess I could write a couple of them out. 2/3. What would be next? 4 times 2 would be 8 over 9, right? And what would be next? 18 over 19, and so forth. Well, let's look at this, what this limit is. So the limit of the terms, again, compare powers, they're the same. I use the leading coefficients, so this limit is 1. So what does that indicate? That means as I get out here, these values are getting closer and closer to 1. I see that already right off the bat, right? 2/3 to 18/19 right off the bat. So think about what that's doing to the sum. When I get out here way down the line, I'm essentially adding 1 each time. 1, another 1, plus 1, plus 1, plus 1. So this thing has to go to infinity if I'm just adding 1 after 1 after 1. And not literally, of course, because it's a limit. But essentially that's what's happening. So what I'm getting at is if you're not having zeros down here, if these aren't zeros way down the line, there's no way this thing can converge. So this is how the test works. The test involves taking this limit of the individual summands. So the test says if the limit to infinity, of course, is not 0, such as the case here, then the series diverges. We've shown divergence for the reasons that were illustrated here. Very, very, very important point is this is called the divergence test because it can show divergence. If the limit happens to be 0, you've shown nothing. The fact that the limit might happen to be 0 is not proof of convergence. Very important point. So this is a relatively easy test to use because a lot of times, I didn't even have to write this to see the limit, right? I can look at that and immediately see that this goes to 1. So if I recognize that, well, I'm doing my solution, I write this out, and I say diverges, that's the analysis, that's the behavior. Why? Divergence test. and I've shown the limit to not be 0, so we're good. So let's see a couple of these. I mean, this is as good of an example as any, to be honest. Let's see what we can come up with here. There, let's see. Okay, we're presented with a series. What does it do? Converge or diverge? Okay, so I won't write that out. You know, this is converge, diverge. That's the question. So let's look at this one. Arctan of n. So this was a fact that we looked at in inverse trig functions. What is the limit of the arctan function as n goes to infinity? If you remember that. Go back to your notes if you need to, but I'll take the limit of the terms and they go to pi over 4. That's clearly not 0. So again, at the end of this summation, I'm adding pi over 4, pi over 4, pi over 4. So I just make my conclusion. Diverges via the divergence test. That's all you need. All right? One thing I'll know is keep in mind that this is one of the easier tests. So what I was getting at before is this should be maybe the first on your list. I look at this arctan n. I know that limit is pi over 4. I know this test will nail it. Again, a lot of what you'll see, this is also useful with a lot of so-called rational functions. This is pretty much the first example. But I look at this immediately and I see the limit of the summands is 3 over 6, which is a half, which is not 0. That's at 3 over 6. I'll just cut to the chase. That's a half. That's not 0. So again, this diverges via the divergence test. Okay, let's see one more. How about our old friend here? Let's do this. 1 over n. So let's say I decide mindlessly to dive in. Oh, it equals 0. Does that show convergence? No, it doesn't show anything. In fact, this is the harmonic series. This diverges. So this fact is completely inconclusive. This series, a series where you get a 0 could converge. It could diverge. The point is, you got to move on. So this is a pretty simple test, but it can only do half for you. It can only show divergence. If the series happens to converge, this is worthless. And you'll move on to some other tests. So keep that in mind. What I recommend, we sort of had a list of integration techniques. I recommend keeping a list of series analysis techniques. And if you have that right now, we have 3 things. This isn't really a technique, it's a series. We have a harmonic series. If we recognize that, we know it diverges. We have a geometric series. If it's a geometric series, we identify the value of r, we make our determination. And we have our first test, the divergence test. Okay? And the good news, I should just throw this fact in, the divergence test can be applied to any series, assuming you can find the limit. Problem is, like we said, it doesn't answer the question every time. Sometimes it's inconclusive. Because what you're going to find later, there's some tests that you can only use in certain situations. But the good news is with the divergence test, you can use it anytime, all the time. And I recommend it as a good first kind of glance. Okay, so in the next meeting, we're going to have some more sophisticated tests. But but we're going to work through them, and I want you to do the homework, right? Practice makes perfect, all right? Have a great day. I got more for you, but still have a great day.